everyone, welcome back. We're learning about semiconductors. In the previous video, we learned about the different types of semiconductors, namely the p-type and n-type, based on the amount of impurities that we add to it. We also saw how semiconductors exist in nature as elements and compounds. We also need to know where are these semiconductors being used. So in this video, I'm going to walk you through the different types of semiconductor devices. Semiconductor devices are broadly classified into three categories: two-terminal semiconductor device, three-terminal and four-terminal semiconductor device. What does this terminal mean? A terminal is a free conductive end of an electronic device or component through which current can either flow in or leave out of the device. In this video, we're mainly going to focus on a two-terminal semiconductor device. Three-terminal and four-terminal, we will be looking into it in the later part of this course. So a two-terminal semiconductor device is a diode. Di meaning two. So diodes have two electrodes, namely the cathode and the anode. The cathode carries a negative charge and the anode carries a positive charge. So this is the symbol of a diode, and this is how a standard diode looks like. There are many types of diode which we'll be seeing later, but just have a rough idea about how a diode looks like. Are you confused that in the previous video we learned that semiconductors are p-type or n-type, and now I'm talking about semiconductor devices that's having two-terminal, three-terminals? Don't worry, we will also look into the composition of a diode. A diode is nothing but a combination of a p-type and n-type semiconductor. And this diode usually conducts current in just one direction and acts as an open circuit or insulator in the opposite direction. Now let's see the characteristics of the diode in the conduction region. There's voltage across the diode is zero and the current is infinite because the diode acts like a short circuit in the conduction region. The characteristics of a diode in a non-conduction region. All the voltages across the diode and the current is zero because the diode acts like an open circuit in the non-conduction region. Moving on, we will see in detail about what is a diode, how does diode work. So as we saw, it is a combination of p-type and n-type semiconductor. The majority carriers of p-type are holes and the majority carriers of n-type are electrons. We know that both p-type and n-type are individually electrically neutral. However, what happens if we combine both of them? Because the majority carriers in n-type are electrons which has a negative charge and the majority carriers of p-type are holes that are positive charge. So when I combine both of them, opposite charges tend to attract each other, and so this transfer of charges between p and n-type, and they try to combine with each other. So how long does this transfer of charge take place? The transfer of charges of electrons in holes take place until an electrical state is formed at this junction that resists further flow of electrons or holes through the junction. Junction is nothing but the point of contact where p and n-type semiconductor meets. So this electrical state that I was talking about is called as the depletion region. So this depletion region ensures that about one point that further transfer of electron from n-type is resisted or repelled by the electrons that exist in the depletion region, and the holes are also repelled by the holes that are present in the depletion region. So now, at this state, the diode becomes electrically neutral without any charge because there's no potential difference and the diode becomes stable. However, if we have to use a semiconductor device in real time, we don't want a device that doesn't conduct electricity. So what do? We could apply a potential difference across the diode. We could apply two types of potential difference across the diode to make it conduct electricity. If we apply a positive potential difference across the diode, it's called as forward bias. If we apply a negative potential difference across the diode, then it is called as reverse bias. So let's go slow and let's see the detail about what is a forward bias. Before moving on to forward bias, this is the general graph of an ideal diode showing the forward bias and reverse bias region, and it is a voltage current graph. You might not understand this graph completely now, but you will understand it when we individually see what is forward and reverse bias. So this is the equation of the conduction in a diode where Vt represents the threshold voltage above which the diode starts conducting electricity, and Nd represents the concentration of donors, and Na represents the concentration of acceptors, where Ni represents the intrinsic concentration, that is, the amount of impurity that we are adding to intrinsic semiconductors. So now we will see about what's forward bias and how forward bias helps in conduction of electricity in the diode. So in forward bias, what we do is we are making it conduct current by applying a positive potential difference by means of a battery. We ensure that the positive terminal of the battery is connected to the p-type and the negative terminal of the battery is connected to the n-type. So, the battery's positive terminal repels all the holes towards the junction because the holes also are positive. Similarly, the negative terminal of the battery repels all the electrons towards the junction because electrons are also negative. So, the depletion region slowly decreases, and there is a potential barrier that is formed at the junction. So initially, the current flow is a little hard. However, when we start increasing the voltage that we apply with the help of a battery, this potential barrier that is created is broken and the charge carriers start to flow and there's conduction of current. So this is what we're talking about, the potential barrier that is created because of forward bias is called as a forward potential barrier. And in a forward potential barrier, the diode starts conducting current only when the applied external voltage is greater than this forward potential barrier. So the forward potential barrier of silicon is 0.7 volts and that of germanium is 0.3 volts. In the earlier part of this course, we also saw that this is one of the reasons why silicon is more preferred than germanium, because germanium has a forward potential barrier of just 0.3 voltage, and so by increasing even little amount of voltage could destroy the germanium crystal. However, silicon crystals are not that easily destroyed, and one other reason is that silicon is nothing but sand, which is abundantly found on earth, and it's very cheap. Now take a look at this picture, which is a voltage current graph of a silicon diode. Now when I keep increasing the voltage, the current flow is initially very high because of the potential barrier that is created at the junction. However, about 0.7 voltage, the silicon diode starts conducting electricity, and so this point is called as the knee point, where the forward potential barrier is completely broken and the diode starts conducting current. So yeah, we've finally come to the end of this lesson. Let's have a quick recap on what we learned in this lesson. In this video, we saw a general idea on different types of semiconductor devices, a 2-terminal, 3-terminal, and 4-terminal semiconductor device. We saw about 2-terminal device having 2 electrodes, anode and cathode. We also saw that a diode could be made into conducting electricity by applying 2 types of potential difference across it, a positive potential called as the forward bias, and by applying a negative potential difference called as the reverse bias. We also saw in detail about forward bias. So, in the next lesson, we will be looking into what is reverse bias and also the different types of diodes. There are many types of diodes like triac, Schottky diode, LED, and a lot more. So yeah, thank you for watching and stay tuned for more. If you have any queries, please ask me in the comment section below.